Okay, let's continue a bit with our exploration of vectors. So specifically 3D vectors. And let's remind ourselves of the unit vectors as they apply to 3D. So this has probably come up when we spoke about 2D vectors in the past. So I say let's have a reminder. So the idea is in 3 dimensions, you've got 3 numbers describing every single possible position. You could also, instead of just representing it in terms of a coordinate, you could represent it as a linear combination of unit vectors. That is to say, a multiple of 3 unit vectors, individual multiples, and then summing that all together. So in this case, the 3 standard unit vectors that we use are I, J, and K. And these have specific values. So you remember in 2D, I was simply 1, 0. Well, in 3D, we just append a third 0 to the third dimension. Similarly, in 2 dimensions, J was 0, 1, and in 3D, we apply a third 0. And then K provides for us the third required unit vector, which in this case is 0, 0, 1. And then it should be fairly obvious that any possible vector you can come up with can be written as a linear combination of these. So again, if we had, say, the vector 5, 2, 3, I could write that as 5i plus 2j plus 3k, and those would in fact be equivalent. Okay, so these are the unit vectors that we use in 3D, I, J, and k. So let's look at an example. So we've been given 2 points in coordinate form, and we're going to find the position vectors in IJK notation. Okay, so for that's really obvious for part A. So remember, the position vector is the vector as taken from the origin to the point A. So we're effectively being asked, what is the vector from O to A? What is the vector from O to B? And in this case, it's quite simple because the origin is 0, 0, 0. So going from 0, 0, 0 to any of these 2 points is equivalent to just taking the value of each dimension and applying the appropriate I, J, or K to it. Okay, so we've got 1 I, 5 J's, and minus 2 K's in the first instance. And in the second instance, O to B, there's 0 I's, there's minus 3 J's, and there's 7 K's. Okay, so it works in the same way as for 2D. That's the nice thing about 3D vectors. It's just an extension of 2D. And then part B, find the vector A to B as a column vector. That we should be fine with. That requires no additional information in terms of this lesson. Take your vector B. I suppose it's good to just practice. Take your vector A, find the difference. The order matters in this case because we're going from A to B. So we're going to do B minus A, and we get minus 1, minus 8, and 5. Oh, sorry, not 5. That's 7 minus minus 2, and 9. Yeah, that makes more sense. Okay, and let's look at another example. So you've been given your 2 vectors A and B, and you're being asked to find specific, and remember the technical term for this kind of expression is a linear combination of 2 vectors. This is a linear combination of A and B, and this one's a linear combination of A and B once again. Okay, quite simple really. It's exactly the same logic as with 2D vectors. Let's just quickly run through it. In fact, I'm just going to write this out and sort of skip I'll just skip for a moment me writing this out. Okay, so that's the first one. You should have got 12 minus 14, 20 if you were trying to do it yourself. And then for the second one, let's take a look at what it would be. Okay, and you'd get minus 8, 0, and 10. Right. Let's look at part B then. State with a reason whether each of these vectors is parallel to 4a minus 5k. So let's remember in 3 dimensions, 4a minus 5k, let's convert that to column because it's easier to work with. That's 4, 0, because there's no j's, minus 5k, 4, 0, minus 5. So the question is asking, remember when we're talking parallel, in terms of vectors, it just means multiple. So are either of these vectors a multiple of this one? Well, it should be fairly obvious, but here's the logic. Looking at the first one, so that's 4a plus b, can I multiply this by a number to get that? And the answer should quite clearly be no, because if I just focus on the first dimension, that 4, to make it a 12, that would necessitate multiplying by 3. Okay, multiply by 3. So if we did that, then the 4 would go to 12, fine, but the 0 would go to 0, which is not minus 14, and in fact that's enough to disprove it. But to just add even further problems, minus 5 times 3 is also not 20. But as long as one of the dimensions doesn't work, then we know it's not parallel. So in this case, not parallel at all to the 4, 0, minus 5. And in this case, quite obviously we can see if I multiplied that 4 by minus 2, I would get minus 8, which is fine. So let's put here times minus 2. And then check it for the other 2 dimensions. 0 times minus 2 is also 0. Minus 5 times minus 2, that's also exactly 10. So therefore, that one is in fact parallel. And the way you'd write that formally as a mathematical statement to say it's parallel is to say minus 8, 0, 10 is equal to minus 2 times 4 minus 2, 0. And that there is a statement which effectively shows that they're parallel because one is a multiple of the other. Okay, done. Okay, let's talk for a moment about unit vectors then. So this is the process by which we convert a vector A to its unit vector A hat. The process, very similar to 2D. So the formula we had for 2D was A hat, the unit vector, is equal to the vector A divided by the magnitude of the vector A. And that applies exactly the same for 2D and 3D. So this is true for 2D and 3D and 4D and 5D and so on. Okay, so let's take a look how that works. In this case, we've got A is equal to, and I'm immediately converting to column vectors, this. The modulus of A, or its size, is therefore equal to the square root of 2 squared plus minus 1 squared plus 4 squared. That's the square root of 4 plus 1 plus 16. That's 21. And then A hat is equal to that vector A divided by the square root of 21. So in other words, 1 over the square root of 21 times the vector 2 minus 1, 4. And you could then, I suppose, put 1 over root 21 inside each of these values here. So you could say it's 2 over root 21 minus 1 over root 21, 4 over root 21, but there's no point because you've got a common factor, quite a complicated common factor, so why not keep it on the outside? So that is effectively your final form. You could also potentially, remember, write this in one alternate form, which is 1 over root 21 times 2i minus j plus 4k. You might sometimes be asked to write it in that form, but this form is also fine. It hasn't specified. So these are two equally valid forms for the unit vector A. Okay, so now let's talk about something new, which is the angle that a vector makes with an axis, and this gets a little bit more complicated in 3D, and let me explain why for a moment it gets more complicated. So let's consider the case for 2 dimensions. If I draw an XY axis, okay, so we're talking 2D for a moment. So we've got XY, this is 2D, and let's mark a point, let's say that point there, and let's find the corresponding position vector. So it's going from the origin to the point, okay, and this is my vector that I'm interested in. And if I ask you the question, what angle does that vector make? I mean, that statement itself is a bit ambiguous, so you need a convention. The convention we're going to go with is with the x-axis. So let's put an angle there, and we tend to call this theta, and that's it. That's the value. And the way you find it is, you know, you're going to do tan inverse of the opposite, which is that length, or the y value, over the adjacent, or the x value of that specific point. So there's only really one reasonable number you can apply when you ask the question, what angle does the vector make with the axis, or the x-axis, as long as you know you're specifying with respect to what. And that's the 2D case. In some sense, we could say this is called theta x, meaning the angle it makes with the x-axis, and then calling this one, what could we call that? We could maybe call that theta y. Okay, but what would the point be exactly? Because wouldn't theta x plus theta y always just be 90 degrees? It would, right? So there's not really, if you talk about the angle it makes with the x-axis and the angle it makes with the y-axis, if you know one, you can get the other. So they're not really, you know, independent values. So we don't bother. We just say, let's just measure it against the x-axis. What's the point? Don't call it theta x, just call it theta. Okay. Now let's think about the case for 3D. How does this compare? So in 3D, as we know, I can only draw a projection of the 3D space. Let's go for something that looks about like that. We've got X, we've got Y, we've got Z. It's 3D, and there's a point out there somewhere, and it has a position vector. And now, if I ask, I want to in some way define an angle. I want some concept, because you know this vector clearly has a direction. The direction is defined, but how can I interpret it as a single angle? And the problem in 3D, unlike 2D, is that one angle is not going to be enough information. You kind of need to know at least more than one angle. So in this case, what we do is we do in fact define 3 different angles. That is to say, the angle that the vector makes with the x-axis, the angle it makes with the y-axis, and the angle it makes with the z-axis. And there will be a relationship between those 3, presumably, but just knowing one of them by itself will not be enough to fully define the direction. Unlike in 2D, where if I know the angle it makes of x, then I know everything I need to know about the direction. Yeah, so here, if you can kind of visualize it, you've almost got, you know, this angle here, that's theta x, and it's a bit sort of slanted. How well can I really draw this? It's hard to visualize, isn't it? That there is your sort of theta z, and then you know, you sort of got this angle here, which is your theta y. Okay, and you can't really say anything like theta x plus theta y adds up to 90 degrees. It doesn't, right? Because you have to kind of visualize it in your mind. This yellow vector, it's not in the plane of xy necessarily. It's leaning into the z direction. So theta x and theta y will not add up to 90, not like the 2D case. And then you've additionally got this theta z. So you have all these three angles. And the question now is, now that we know, what I mean by their definition, can we come up with a kind of formula or easy way to calculate them? And fortunately, we can. So this is how that goes. Let's just make some space. Okay, so in general, for a vector, let's say position vector, okay, so going through the origin, oh, in fact, we don't need to necessarily say position. The angle will still be the same. So for a vector, x, y, z, okay, so in this case, x, y, and z are specific values. The angle it makes with the x-axis is equal to cos inverse of the x value divided by its size, that is to say the size of the vector, the magnitude of the vector. In fact, let's give the whole vector a name just to make this a little bit more concise. So let's call the whole vector A. Okay, for a vector A, which is defined as x, y, z, theta x equals cos inverse of x divided by its magnitude. So that's magnitude of A. And this is more concisely, or not more concisely, maybe more neatly written as cos theta x equals this. Okay, so you could see how applying cos inverse to both sides will give you the actual value of theta x. And now, if you've remembered that, you've basically got the formulas for the others. Cos of theta y is the y value divided by the magnitude, and cos of theta z is equal to the z value divided by the magnitude. Okay, that's that simple. So those are the three formulas, really just one formula, which allows you to find the angle that a 3D vector makes with any one of the three coordinate axes. So let's look at a specific example. Here's how we do the working for this. We've got a vector 2, minus 3, minus 1. And we want to find the angle it makes with each of the positive coordinate axes to one decimal place. So you're looking for three numbers. Effectively, the question is asking, what is theta x, what is theta y, and what is theta z? Okay. To do that, let's first just find the magnitude of this vector, magnitude of A. So can we do that in our heads? 2 squared is 4, minus 3 squared is 9, minus 1 squared is 1. Add that all up, I get 14. Take the square root, it's the square root of 14. Therefore, I can immediately write cos theta x equals 2 divided by root 14. Cos theta y is equal to minus 3 divided by root 14, and cos theta z is equal to the z coordinate minus 1 divided by root 14. Implies, theta x equals, theta y equals, theta z equals, and now you just need to apply cos inverse to both sides of these equations. So cos inverse of 2 over root 14, cos inverse of minus 3 over root 14, cos inverse of minus 1 over root 14, and you'll get three decimal numbers, which will give us our final answers. In this specific case, the answers we get are theta x is equal to 57.7 degrees to one decimal place, theta y is 143.3, and theta z is 105.5. Notice that these formulas are really useful because we don't have to actually think too hard, in the sense that whether there's a minus or not, whether your ratio here is a negative number or a positive number, you just do cos inverse on your calculator, you'll get the appropriate angle. The calculator will just give it to you. Okay, and now let's look at a sort of problem solving kind of question. We're given 2 points, A and B, and a third point, which is just the origin. And we're told that, well, we're going to be asked to find AB as a vector. We can do that later. But we're being really asked to show that this triangle made up of the 3 points, origin, A and B, is isosceles. So all we really need to prove is that either 2 of the angles or 2 of the lengths are the same. Presumably lengths would be easier to do. Let's just graph out, not really particularly precisely, but just the relationship between all these points. So we've got an origin O, we've got A, let's just throw it up here, and then I don't actually know which of the 2 sides are the same length, so actually I'm just going to make it kind of any triangle. So it almost looks equilateral, I suppose, but I have no idea what the lengths of these various things are. But I do know that the coordinates are 0, 0, 0, are 4, 2, and 7, and 3, 4, and -1. And the triangle we're talking about is the triangle formed by connecting these 3 points together. Okay. So when it says here find AB, this one, presumably that's just because it wants us to find out the length of this third side. Let's do the 2 other sides first, though they'll be a bit easier. So this first side, O to A, its length is going to be 4 squared plus 2 squared plus 7 squared, all square rooted. Let's do that on the calculator. And what do I get? I get square root of 69. And this lower length here, OB, that's 3 squared plus 4 squared plus -1 squared, square rooted. What's that? The square root of 26. Yeah. Okay, so these 2 sides did not turn out to be the same length, even though I've drawn them that roughly that way, but doesn't matter. They're not the same length. Therefore, if we're going to show this thing as isosceles, we need to find this length, and if it ends up being either root 26 or root 69, then it's isosceles. And if it's neither of those 2, then it's not isosceles. So let's find out the length for this one. And that's just the length between A and B, which is, you know, the difference between the coordinates and then the usual magnitude of that. So that's why it's asking us to find AB. Let's do that briefly then. Any direction doesn't really matter. I know it said from A to B, but oh fine, I suppose we should do it in the order it says. A to B, so that's B minus A. Alright, fine. If we're working in a world of exam technique, let's do what it actually says. B minus A. So that's 3 minus 4 is -1. 4 minus 2 is 2. And I've written that poorly down there. -1, -7, that's -8. Okay, so let's find the magnitude of that. The magnitude of -1, 2, -8 is the square root of 1 squared plus 2 squared plus 8 squared. I've cheated there slightly. I didn't write the minuses, but it doesn't actually matter, as you know. So -1 squared, or 1 squared, plus the 2 squared, plus the 8 squared, gives me 69. Okay, that makes sense. So it's equal to root 69. So we have root 69 here. So therefore, OA, the magnitude of OA is equal to the magnitude of AB. Therefore, the triangle OAB is isosceles. Okay, and we're done. Right, so time to try some questions yourself. Looking at this one. This one is not too bad. You're just effectively solving a set of equations. So see if you can knock this one out quickly. Pause the video now. And there's your answer. And for our next question, this is a bit similar to the last example we did, except you're just finding the values of certain things that they're asking for. No proof actually required. Again, just make sure you can knock it out quickly to be able to comfortably get these values. When you're ready, pause the video now. Okay, and there are your answers there. Given in terms of I, J and K, column vectors are of course fine unless it's specified. Oh, it did specify, my mistake, sorry. So you can do your working in column vectors, as you know, I would suggest, but your final answer must be in terms of I, J and K, at least for 9A. Great, next question. Here you're just trying to find the unit vectors. So I guess it's a bit of practice of surds and making sure you are able to comfortably find unit vectors. You can pause the video now. Okay, and there are your answers. Slightly unwieldy numbers. For example, part A, I would have personally written that as 1 over root 29 bracket and then 3i minus 4j minus 2k. I'm sure you can get away with that. It seems unreasonable to not be able to write it in that sense. And likewise for B and C, you can take out a factor of a fifth and take out a factor of a quarter and just write it on the outside with a very large bracket surrounding the rest. Okay, question 14. Bit more investigation here now. Particularly part C, we're going to have to think a little bit about how you find that angle. Okay, so give that a go. Pause the video now. And here are your answers. It was in fact 45 degrees. So I can presume from that then if it's 90, 45, the other must be 45. Should be an isosceles triangle, which makes sense because two of the sides are the same length. Okay, and then your challenge. So you've got now for your first sort of introduction to this concept of a plane, I suppose, or at the very least within this topic, you've got a vector A and it's asking you the angle it makes with the xy plane. So remember, that's not the same as the angle you make with the x-axis or the angle you make with the y-axis. Remember, the plane is kind of like the 2D shape. So if I just briefly draw this out, if you've got your x, y, z sort of 3D space, then the x, y plane, if I take that as x, that as y, and that as z, your xy plane is kind of like the infinite plane, if I shade it in, but you know, infinitely in all directions. Okay, and then this vector, minus 2, 6, minus 3, what angle does it make against this? So that's going to take a little bit of thought. Remember, whenever you've got a vector, you can just think of it as a triangle almost, with reference to whatever it is you're interested in. So try and make a triangle out of this vector and sort of leaning against this xy plane and see if you can find what that acute angle would be. So give that a go. When you're ready, pause the video now. And that would be your answer, 25.4 degrees.